Okay, let's unpack this. You've heard it everywhere since grade school.
Yeah.
Oil and gas are fossil fuels.
Right.
They come from ancient plants and animals, buried deep for millions of years, cooked into hydrocarbons. It feels like one of those, settled facts of the world, right?
Well, that conventional understanding,
Uh-huh.
the biogenic theory, it's certainly the dominant explanation,
Yeah.
especially for the vast majority of the oil and gas reserves we actually tap into today.
Yeah.
It's really well supported by evidence, particularly in sedimentary basins, linking hydrocarbons directly to organic matter.
But what if that's not the whole story? What if Earth has another source entirely hidden way, way deeper than any dinosaur ever roamed?
hmm
We're doing a deep dive today into a source that pushes back on the idea that all hydrocarbons come from fossils.
Exactly. The source we're exploring is the abiogenic theory of hydrocarbons, revisiting the deep origins of Earth's energy resources
Mm.
by Douglas C. Yvonne. And this paper, it really dives into the evidence for the abiogenic theory, which suggests hydrocarbons can also form from, well, inorganic materials and processes
Yeah.
deep within the Earth's mantle and crest,
Completely separate from biology.
completely independent of biological activity. Yeah.
So forget ancient forests and plankton for a second. This theory is saying hydrocarbons can just sort of make themselves down there.
That's the core idea.
Our mission then is to look at the surprising evidence the source pulls together. What's the fundamental difference between the two ideas? Can you break that down?
Sure. Well, the biogenic view you mentioned, that's all about organic matter, right? Buried in sediment, add heat, add time, usually in relatively shallow crustal basins.
You're right, the standard story.
The abiogenic theory, though, it posits that you can start with simple inorganic compounds, things like carbon dioxide, water, minerals, stuff found in the deep earth.
Okay.
And under extreme pressure and temperature, these can react to form hydrocarbons, methane, ethane, possibly even heavier ones.
Wow, it completely changes the origin story. So it's not just a different recipe, it's like a different kitchen entirely.
Yeah,
Way deeper.
precisely. And the source argues that this deep inorganic process isn't just theoretical. There's growing evidence that it actually contributes to Earth's hydrocarbon reservoirs.
Contributing. Or even more.
Well, maybe even providing a mechanism for replenishment in some areas.
Okay, replenishment. That's a bold claim. We'll have to get into that. Where does the source start building its case? I mean, how do scientists even begin to test an idea about processes happening, thousands of kilometers down?
Yeah, it's a challenge. They
Yeah.
start in the lab. One key line of evidence comes from experiments designed to simulate the extreme conditions of the Earth's mantle.
Okay, simulate the mantle. That sounds intense. What kind of conditions are we talking about here? Pressure-wise? Temperature-wise?
We're talking pressures that are thousands, even tens of thousands of times greater than what we experience at the surface. Think 5 to 10 gigapascals. That's huge. And temperatures ranging from, say, 500 up to maybe 1500 degrees Celsius. Very hot.
And how do they even do that?
They use specialized equipment, things like diamond anvil cells, high-pressure presses,
Yeah.
basically ways to crush tiny samples under immense force while heating them precisely.
Okay. And what materials are they crushing? Are these like exotic things or stuff we actually think is down there?
Good question. The experiments mentioned in the source, including work by people like Kucherov, they use simple materials believed to be abundant in the mantle.
Like what?
Things like calcium carbonate, basically limestone, water, iron oxide rust, essentially.
Yeah.
Just basic rocks and water, stuff we know is down there.
And they put basic rocks and water under this insane pressure and heat, and hydrocarbons come out without any ancient organic gunk mixed in.
That's the really key finding. Yes, they successfully synthesized hydrocarbons, primarily methane, CH, that's the simplest one, but also heavier ones like ethane and propane, directly from these inorganic precursors under those mantle-like conditions.
Wow, so we can literally make hydrocarbons in a lab just by squeezing and heating dirt and water really, really hard. That feels like a pretty fundamental proof against the idea that life is the only way.
It is. It proves that the formation of hydrocarbons from inorganic materials is thermodynamically possible and geologically plausible under deep Earth conditions.
You're right.
Methane, at least, doesn't require fossil origin. And the fact they could form components found in liquid petroleum suggests the process could potentially extend to heavier hydrocarbons, too.
But okay, my skeptical brain immediately goes, just because you can make it in a tiny lab doesn't mean it's happening on a massive scale inside the whole planet. Does the source address that kind of scaling issue?
It does, absolutely. The source acknowledges that scaling these lab findings to the Well, the vastness and complexity of the mantle is challenging,
Sure.
and the exact scale of natural production is definitely debated. Lab conditions can't perfectly mimic geological timescales or the complex fluid dynamics over millions of years. But the experiments demonstrate the fundamental chemistry is sound.
Ah,
The possibility is there.
got it. Proof of concept in the lab. So where does the source look next for evidence that this is actually playing out in the real Earth, not just in a tiny diamond cell?
Well, the source points to geological observations. Basically, finding hydrocarbons in places where, according to the traditional biogenic theory, they absolutely should not be.
Okay. Like where?
Specifically, in igneous and metamorphic rocks.
Okay. Igneous, like volcanic rock, metamorphic, is rock changed by heat and pressure.
Mm.
Why is finding oil or gas in those rocks such a big deal?
Because think about how they form. Igneous rocks solidify from molten rock, magma, or lava, incredibly hot. Metamorphic rocks are formed under intense heat and pressure deep underground.
Right, not exactly hospitable for old plants or algae.
Exactly. These are environments where organic matter, the basis of fossil fuels, would have been either completely destroyed by the heat or simply wasn't present to begin with.
Ah, okay.
So finding hydrocarbons trapped within these rocks, far from any sedimentary layers, is a strong indicator of an abiogenic origin. It suggests they formed within or migrated through these deep, hot rocks.
So you're finding oil fingerprints in the wrong kind of crime scene, geologically speaking.
That's a good way to put it.
Yeah.
Precisely. The source highlights, for instance, ultramafic rocks derived from the mantle itself, like peritites and serpentinites.
Serpentinites.
Yes, and they are frequently associated with methane and hydrogen. The source cites examples in ophiolites. These are segments of oceanic crust and mantle that have been sort of thrust up onto continents.
Right, I've heard of those.
In places like Oman, the Philippines, Italy, these ophiolites often contain these gases trapped within the rock.
And is this often linked to that process you mentioned earlier, serpentinization?
Yes, serpentinization is really key here. It's a specific chemical reaction between water and these iron-rich ultramafic rocks, usually at moderate temperatures, maybe 200, 400 degrees Celsius.
Okay.
And this reaction produces hydrogen gas. And it creates conditions that are just perfect for forming methane from carbon compounds already present in the rock, like co-uro or carbonates. It's like a natural underground factory for abiogenic methane.
So water plus certain deep rocks equals methane and hydrogen, and this is happening today.
Absolutely. We see direct evidence of this happening right now at places like the Lost City hydrothermal field. It's on the Mid-Atlantic Ridge.
I'll say right.
Yeah, the methane emissions there are directly tied to this serpentinization process, and scientists have confirmed it's not biological.
Wow.
The source also mentions hydrocarbons found in tiny gas bubbles, inclusions within deep granitic rocks, and also in metamorphic rocks from big mountain ranges like the Alps. Again, places where you wouldn't expect traditional organic sources.
Okay, so we have the lab showing it's chemically possible, and we're finding hydrocarbons in rocks where they shouldn't be if the fossil theory was the only game in town. What about movement? Are these deep earth fluids getting out?
That leads right into the next line of evidence. Hydrocarbon emissions coming from deep tectonic zones.
Tectonic zones,
That's
like
right.
fault lines, earthquake zones.
Exactly. These are the really active regions where earth plates interact, major faults, rift valleys where continents pull apart, subduction zones where one plate dives under another.
Okay.
Crucially, these zones act like plumbing systems. They provide the deep fractures and pathways that can connect the mantle and deep crust all the way up to the surface.
And hydrocarbons are essentially leaking out of these deep cracks, like natural gas seeps?
Yes. The source points to persistent seeps and emissions of methane and other light gases in many of these areas.
Can you give some examples?
Sure. Deep faults in the Gulf of Mexico show natural gas seepages linked to these deep systems. Methane seeps along tectonic lines in the Black Sea. And as we just talked about, significant methane and hydrogen coming from hydrothermal vents along mid-ocean ridges. Lost City is a prime example.
Yeah.
You also see methane-rich seeps and subduction zones, like off Japan or Cascadia, and in continental rift zones like the East African Rift. Even along transformed faults like the San Andreas.
So the planet's geological hotspots, the really active places, are basically venting these deep source hydrocarbons.
Yeah.
That feels hard to explain with just shallow, buried forests from millions of years ago.
It is. The location of these emissions, often directly correlated with these deep fault systems that clearly access mantle processes or the deep crust, strongly suggests a deep origin and a migration pathway upwards. That's a core tenet of the abiogenic theory.
Okay, that's indirect evidence from seeps on the surface or seafloor. Have we ever, like, gone down there and found hydrocarbons in the deep crust directly through drilling?
Yes, and this is another really powerful piece of evidence discussed in the source. Findings from deep drilling projects. When we actually drill way, way down.
Okay.
The most famous example cited is the Kola super deep borehole in Russia.
Right, the one where they drilled over 12 kilometers down. That's incredibly deep. What did they find way down there?
Well, at that incredible depth, they were drilling into ancient crystalline basement rocks, granites and gneisses, not sedimentary layers where you'd expect fossils.
Right.
And they found hydrocarbons, including methane, trapped within those crystalline rocks.
Wow.
These rocks are kilometers below where any traditional organic material could possibly exist or, frankly, survive the heat and pressure.
Going past any reasonable depth for fossils and still finding hydrocarbons, that seems pretty compelling evidence, doesn't it?
It's considered a very direct challenge to the idea that hydrocarbons are only found in sedimentary basins derived from organic precursors.
Were there other projects like that?
Yes. The source mentions the German KTB project, which drilled over 9 kilometers, also found hydrocarbons in crystalline basement. Deepwater drilling in places like the Gulf of Mexico has found hydrocarbons in deep igneous or metamorphic rocks below the conventional reservoirs. Even drilling into the Chicxulub impact crater found hydrocarbons in fractured crystalline rocks unlikely to be biogenic.
Yeah.
It really strongly supports the idea that hydrocarbons can form much deeper than we typically think and then migrate upwards.
It definitely forces you to reconsider the whole fossil part of fossil fuels, at least for some of these occurrences. What about looking even further out? Does looking at other planets help us understand Earth's deep interior?
Absolutely. This is a fascinating angle. The source highlights the widespread evidence of hydrocarbons found throughout our solar system
Yeah.
on bodies where life, as we know it, almost certainly does not exist. This provides crucial comparative evidence that hydrocarbons can and do form abiotically. It's not just an Earth thing.
Like, where are we seeing them? Give me the tour.
Okay, well, the most famous example is Titan, Saturn's largest moon. It's got an atmosphere thick with methane and ethane.
Right, the methane lakes.
Exactly. It has actual lakes and rivers of liquid methane and ethane on its surface. The source points out these aren't from biology. They likely form through photochemical reactions driven by sunlight in the atmosphere and also potentially from subsurface geological processes, maybe involving water-rock reactions inside Titan.
Okay, that's mind-bending. Lakes of hydrocarbons on a moon with no life. If it can happen out there without biology, why wouldn't similar inorganic processes happen deep inside Earth?
Precisely. That's the argument. It strengthens the plausibility of abiogenic formation right here on Earth.
Where else?
Well, Jupiter and the other gas giants have massive amounts of methane in their atmospheres. That's thought to be primordial, left over from the solar system's formation, or formed under their immense internal pressures and temperatures from hydrogen and carbon. Even Mars. The Curiosity rover and orbiters have detected puffs of methane. One potential origin being discussed is serpentinization, that same water rock reaction we talked about happening on Earth, possibly occurring beneath the Martian surface. And you find hydrocarbons on comets, on dwarf planets like Pluto and Ceres. Complex organic molecules, methane, ethane, likely formed abiotically in the cold outer solar system or through early chemical processes.
So the conditions we think might be making hydrocarbons deep inside Earth, high-pressure water-rock interaction, we see variations of those conditions creating hydrocarbons elsewhere in the solar system without life.
We do. The universe basically shows us that hydrocarbons are natural chemical compounds, not just the exclusive product of earthly life. This makes the idea of a significant non-biological source on Earth much more credible.
Okay, let's bring it back to Earth. We talked about seeps, hydrocarbons leaking out. What about gases coming more directly from the mantle itself?
Right. That brings us to mantle outgassing. This is the actual release of gases and fluids from the deep Earth, primarily through things like volcanic activity, mid-ocean ridges, and these serpentinization zones we keep mentioning.
So volcanoes are burping up methane.
Sometimes, yes. The source notes that volcanic gases from well-monitored places like Mount Etna in Italy or Kilauea in Hawaii often contain trace amounts of methane alongside the more common gases like water vapor, QO-Uros, sulfur dioxide, hydrogen sulfide.
And those high temperatures and pressures inside the volcano rule out that methane coming from, say, shallow organic matter getting sucked in and cooked.
Pretty much, yes. The conditions where magma forms are so extreme, Any shallow organic material would be instantly vaporized or oxidized. The methane seems to be coming along for the ride from deeper source regions.
Okay.
And again, those deep-sea hydrothermal vents we discussed,
Mm.
especially the ones driven by serpentinization like Lost City, they're another prime example of hydrocarbons being actively vented directly from deep geological processes happening now.
It's another piece connecting the deep earth, the mantle, to the hydrocarbons we see closer to the surface.
It is. It provides direct observation of their release from depth. And speaking of gases with deep origins, the source also highlights the interesting association of hydrocarbons with certain other gases, particularly helium, found in oil and gas reservoirs.
Helium. Like for party balloons, how does that link to oil? Seems unrelated.
Well, certain isotopes of helium act as really good tracers for deep Earth processes. You see, helium comes in a couple of main forms, isotopes. There's helium-3, which is mostly primordial. It was trapped inside the Earth when the planet formed and is more abundant in the mantle.
Okay.
Then there's helium-4, which is constantly being produced by the radioactive decay of uranium and thorium in the Earth's crust and mantle.
Right.
Now, finding helium, especially helium with a high ratio of helium-3 to helium-4, a mantle signature mixed in with oil and gas is significant. Why? Because helium is an inert gas. It cannot be produced biologically.
Ah, okay. So if you find oil or gas that's kind of blended with a gas that scientists know only comes from the deep mantle, that's a pretty strong hint about where the oil might have traveled from, isn't it?
It's considered a powerful geochemical clue. While the helium itself isn't a hydrocarbon, finding alongside oil and gas, particularly with those isotopic signatures pointing to a mantle source, well, it's very consistent with those hydrocarbons having migrated from great depth.
It came up together.
Potentially, yes.
Yeah.
Migrating together, possibly alongside other mantle-derived gases like hydrogen or QUO. The source mentions several helium-rich gas fields around the world, like the Hugoton field in the U.S., fields in Russia, the Middle East, often located in tectonically active areas where you have pathways from the deep earth.
It's like finding a deep-sea fish washed up in a mountain lake. It strongly suggests a connection, a pathway, a journey from a deep source, even if you didn't see the journey happen.
That's a great analogy. It's definitely circumstantial evidence regarding the origin of the hydrocarbons themselves, but it's strong evidence supporting their migration from depth, which fits the abiogenic model.
Okay, let's circle back to the fundamental physics and chemistry for a second. Even if these hydrocarbons can form deep down, can they even survive those intense pressures and temperatures inside the Earth over geological time? Wouldn't they just break down?
That's a crucial question, and it brings us to the evidence for thermodynamic feasibility. What does the chemistry say?
Yeah.
The source explains that under the extreme conditions of the deep crust and upper mantle, those really high pressures and temperatures we discussed, hydrocarbons, particularly methane, are actually predicted by chemical models to be thermodynamically stable.
Stable, meaning they don't just fall apart instantly.
Exactly. They don't just decompose. In fact, their formation can even be energetically favorable under certain mantle conditions. They can exist and they can persist.
So the laws of physics and chemistry say they can form and they can hang around down there.
Yes. Theoretical calculations, computational simulations like molecular dynamics, and importantly, those high-pressure lab experiments we talked about earlier, they all confirm this. They show methane formation is possible and that it and potentially heavier hydrocarbons can remain stable under those conditions.
That's really crucial, isn't it? Because without stability, none of the other evidence, the seeps, the rocks, it wouldn't really matter if the stuff couldn't survive the journey or exist at depth.
Absolutely. It makes the whole idea physically viable according to the laws of chemistry. It provides the essential how it could exist and persist piece of the puzzle.
Okay, so we know we can drill down and sign things, but beyond drilling, how else do we kind of see or map or infer what's happening deep underground, especially related to fluids?
Right. We can't drill everywhere. That's where geophysical data comes in, providing large-scale, albeit indirect, evidence. Techniques like seismic surveys are key.
Like using sound waves to map the Earth, like an ultrasound.
Exactly like an ultrasound for the planet. We send sound waves down and listen to how they bounce back or travel through different layers. Now, fluids like water, or potentially hydrocarbons, have different physical properties than solid rock.
How so?
They tend to slow down seismic waves. So detecting regions deep down where seismic waves travel unusually slowly, these are called low-velocity zones, or LVZs, can indicate the presence of fluids or even partial melts. Fluids can also increase the electrical conductivity of rocks.
So we can use these methods to basically find signatures like echoes or conductivity changes that suggest pockets of fluid or pathways for fluid flow deep down.
Precisely. Geophysical surveys detect these kinds of anomalies, seismic signatures consistent with fluids, high conductivity zones often in deep crustal or even upper mantle rocks. And interestingly, they often find these anomalies in locations near tectonic zones, places where abiogenic formation and migration are hypothesized to occur.
So in places where you wouldn't necessarily expect conventional oil based on the old model, but where this deep theory says fluid activity might be happening.
Yes, they detect these potential deep fluid reservoirs. Sometimes they can even map features using something called seismic anisotropy. That's variations in wave speed depending on direction, which can suggest networks of fluid-filled fractures and faults. These sometimes appear to connect deep zones to shallower crustal levels. The source cites examples from beneath mid-ocean ridge hydrothermal systems like Lost City, anomalies in subduction zones, rift zones like the East African Rift, and deep structures under basins like the Caspian Sea, suggesting deep fluid systems.
It's like getting a blurry map of the deep Earth's plumbing system, potentially showing where fluids are accumulating and moving.
That's a good way to put it. It's not a direct picture of hydrocarbons, but it provides the large-scale subsurface context. It shows deep fluids exist and move in ways consistent with the abiogenic theory.
And finally, one of the most fascinating, almost unbelievable pieces of evidence mentioned in the source, these reports of oil and gas fields refilling. Is that real?
This is perhaps the most intuitively compelling observation for many people, and certainly one of the most debated. There have been reports, documented over decades in some cases, from certain oil and gas fields around the world.
Oh, where?
Including areas in the Gulf of Mexico. The Caspian Basin giant fields like Tengiz and Kashagan are mentioned some Middle Eastern fields, even places like Kern River in California.
Okay, and what's happening there?
The observation is that production has been sustained much longer than initially expected based on reserve estimates calculated using the traditional model. Or in some cases, reservoir pressures seem to recover or even increase after periods of depletion.
Wait, fields that should be running on empty seem to be getting recharged? How does the traditional theory even explain that?
Well, under the strict biogenic model, a reservoir is basically a finite tank of ancient hydrocarbons trapped in rock.
Right.
Once you pump it out, it should stay depleted, unless maybe you discover a previously unknown section of the tank or improve extraction. The abiogenic interpretation, presented in the source, is that this observed replenishment is potential evidence of a continuous or ongoing supply of hydrocarbons migrating upwards from deep Earth abiogenic sources.
How?
Through those deep fault systems we talked about, effectively recharging the shallower reservoir from below over time.
So the Earth isn't just storing ancient fuel in these spots. It might actually be making more deep down and piping it up.
In certain specific geological settings, that's the interpretation abiogenic proponents offer. It's a very provocative idea. And the fact that these reports often come from tectonically active regions, areas with known deep fault systems, aligns with this idea of deep migration pathways being active.
Okay, let's try and pull this all together. It's a lot of different kinds of evidence. The lab experiments say the chemistry is possible.
Right.
We find hydrocarbons in igneous and metamorphic rocks where they shouldn't be, biologically speaking.
Yep, biological evidence.
We see seeps and mantle outgassing showing stuff is coming up from deep zones, especially tectonic ones.
Migration pathways.
Deep drilling directly confirms hydrocarbons exist way down in crystalline basement rock.
Direct detection.
Other planets and moons show hydrocarbons form naturally all over the place without life.
Comparative planetology, yeah.
Thermodynamics says they're stable down there. Helium acts as a tracer, suggesting deep origins for associated fluids.
Physics and geochemistry agree.
Geophysics kind of sees the plumbing, the deep fluid systems and pathways.
Indirect imaging.
And then maybe, just maybe, some fields are actually refilling over human timescales.
The replenishment observation, yeah.
Yeah.
That's quite a collection of threads pointing in a similar direction, isn't it?
It is.
The cumulative weight of evidence presented in the source really suggests that abiogenic hydrocarbon formation isn't just some fringe hypothesis. It seems to be a real, scientifically supported process that likely contributes, perhaps significantly in places, to Earth's total hydrocarbon inventory.
It's backed by observations across a lot of different scientific disciplines.
Exactly. Geochemistry, geophysics, geology, planetary science, experimental petrology.
So what does this all mean for us? For energy? For how we see the planet itself? What are the implications?
Well, they're potentially huge. If abiogenic processes contribute meaningfully, It could, for instance, expand the potential areas for hydrocarbon exploration. You wouldn't only look in sedimentary basins.
Where else?
You might look more closely at deep tectonic zones, crystalline basement rocks near major faults, deep fault systems themselves, areas previously overlooked by conventional exploration models.
Could lead to new discoveries, maybe.
It could. It also highlights the importance of the Earth's deep carbon cycle. It suggests there's dynamic carbon chemistry happening far below the surface, involving the mantle, not just in the biosphere, oceans, and atmosphere where we usually focus.
Well, like carbon isn't just on the surface.
And it fundamentally changes, or at least challenges, the idea of hydrocarbons as purely finite fossil resources if this replenishment is happening significantly in certain areas.
Potentially more sustainable in those specific spots.
Over geological timescales, perhaps, in specific geological settings where continuous migration occurs. It challenges the strict finite label we always use. It doesn't mean oil will never run out globally, not at all, but it opens up possibilities for certain regions and changes the long-term resource perspective.
And it connects Earth to other planets, too.
Yes, it deepens our understanding of planetary processes, showing similar abiotic chemistry might be at work inside Earth, as we see on places like Titan or early Mars.
Now, to be clear, the source isn't saying the biogenic theory, the fossil fuel theory, is completely wrong for everything we use today, right? It's not throwing that out.
No, that's a crucial point of balance. The source definitely emphasizes that the majority of the hydrocarbons we commercially exploit today are still best explained by the traditional biogenic theory.
Okay.
The evidence for an organic origin in those vast sedimentary basins is really robust for most conventional oil and gas reserves. The argument in the source is more for coexistence.
Coexistence, meaning both happen.
Exactly. That abiogenic processes are a real, perhaps underappreciated contributor, especially important in geological settings lacking organic source rocks, or maybe acting as that replenishment mechanism for some existing biogenic reservoirs.
So it's less an overthrow of the old idea and more of an expansion, adding another layer to our understanding.
I think that's a good way to put it. It's adding another layer of complexity to the Earth's incredibly dynamic systems. But there are still major challenges, for sure.
Like what?
Well, quantifying the exact global contribution of abiogenic versus biogenic hydrocarbons, that's a huge ongoing task. Really difficult.
I can imagine.
And definitively linking specific hydrocarbons you find in a reservoir back to a deep mantle formation process rather than just deep migration from maybe a deep crustal biogenic source. That requires very specific, complex geochemical fingerprinting that's often hard to obtain or interpret unequivocally.
So more research needed, basically.
Always. But the evidence presented for abiogenic formation and deep migration as real geological processes is compelling and growing.
It definitely makes you look at the ground beneath your feet a little differently, doesn't it? Thinking about what might be cooking deep, deep down.
It certainly challenges our conventional understanding and opens up some really fascinating possibilities about the deep hidden workings of our planet.
So we dove deep into the surprising idea that maybe not all hydrocarbons are the result of ancient life, not strictly fossil fuels. The evidence, from high-pressure labs mimicking the mantle to unexpected finds in deep rocks, to continuous seeps leaking from tectonic zones, drilling deep into the planet's crust, looking at hydrocarbons on other worlds,
Right.
the gas emissions coming from the mantle, those helium clues, the physics saying it's stable, and even this potential for reservoirs refilling. It really paints a picture of a dynamic Earth, one where hydrocarbons might be continuously generated from within, from inorganic stuff.
It certainly does. It suggests a much more complex and, frankly, dynamic origin story than the simple fossil fuel narrative we usually get.
This whole deep dive, it really makes you wonder, if hydrocarbons can form continuously deep within the Earth through these inorganic processes, what does that fundamentally change about our long-term energy future, at least in certain regions? And maybe even more profound, what other surprising secrets might Earth's deep interior hold? What other fundamental processes are happening down there that could completely change our understanding of the planet that we haven't even considered yet?